Hello, my name is Thora Petersen, and I am talking about Gibbs free energy, which I believe is lecture 35. Okay, so in order to talk about Gibbs free energy, we first have to talk about what a spontaneous process is. And a spontaneous process is a process that once started, it continues on its own and it doesn't need outside intervention. So an example of this would be a match. Like once you strike it, it continues to burn by itself. And I think a homework example is soup. Like if the soup will continue to get cold if you leave it on its own. A non-spontaneous reaction, it needs intervention. So for an example, a phone will go and repair itself on its own. You need to go and get it fixed at a store. And this has to do with Gibbs free energy being a state function, which we'll talk about later. Okay, so this is the equation itself. It was found by J. Willard Gibbs, and I believe he was one of the first people to get his PhD at an American university. So Gibbs free energy is the energy available to do work. This equation helps us to know when endothermic and exothermic reactions will be spontaneous and why some are and some aren't. It also tells us if it is a spontaneous, but it doesn't tell us for how long that reaction happens. And then also it doesn't mean it will happen. So just because we can get that number and if it's positive or negative, it doesn't necessarily mean that the reaction will happen, but we can just predict if it does happen and whether it'll be spontaneous or not. Okay, so three main things that are useful to remember when looking at Gibbs free energy are the units, which are joules over moles. Another thing is that it's a state function, which means we care about the reactants and the products. We don't really care about the journey along the way. I think in class we talked about for the state function, if you're driving or flying, or I'm trying to remember now. So a state function, it just doesn't matter how you're getting to a certain place. It's only the beginning and the end that matter. And then also another thing to remember is that we use enthalpy and entropy. Okay, so what makes it spontaneous and what determines if it's not spontaneous. So if delta G is less than 0, so if it's negative, then it's going to be spontaneous. And if delta G is greater than 0, then it is not spontaneous. Sorry, I just want to make sure this is recording. Okay, good, sorry. Yeah, so if delta G is greater than 0 or positive, then it's not a spontaneous reaction. And then if delta G equals 0, then the system is in an equilibrium, but this is not very common, and we'll kind of talk a little bit more about it later as well. So what does each thing stand for as well? Delta G is determining whether it's spontaneous or not. It's the free energy, Gibbs energy, and it's what's left to do useful work. And it's basically whether we have energy or not to make it spontaneous, a spontaneous process. Delta H is whether it's endothermic or exothermic, and it's the total energy of the system exchanged in a process. And then T is obviously the temperature, and delta S is the disorder within the system, and together it's the proportion of this energy converted to entropy, portion of energy lost to do other things. So how do we know then from this information whether a reactant is going to be spontaneous or not. So if we have a negative delta H and a positive delta S, it's always going to be spontaneous and it's always going to be less than 0. And that's just saying if we have heat leaving the system here, and we have if we have heat leaving here and we have a spontaneous chaos going on, then we're going to have a spontaneous reaction. And then down here, if we have heat entering the system and we have less chaos going on, then it's not going to be spontaneous. And I kind of have an analogy to remember the middle two, if it's helpful. But let's see if you guys can see this. Let's say that you're at the beach with your friends. For drawing, and you go from laying on the towel to being in the water. Sorry for this very poor drawing. And you stay there all day. So from when it's very, very hot to when the sun's going down. Okay, so the ideal time to be laying on the beach, sorry, I'm not sure if you can see this or not. You can. The ideal time to be on the beach is when the temperature is low. It's when it's going to be relaxing and somewhat warm. And the time to be in the water is when you want to have fun, when it's really hot outside. Fun, aka chaos, or disorder, and when energy is being used. So when the temperature is low, and when it's relaxing, and when there isn't disorder, it's going to be spontaneous at a lower temperature. And then when energy is being used and when it's chaotic, there's a lot of disorder. And when the temperature is high, this is when it's spontaneous at a lower temperature. So that is my analogy. Let's see if you can see the work. Yeah. Basically, when this is a negative number, if this is still a relatively low number and it's also negative, it'll still come out to be a negative number, meaning that it can still be spontaneous. But if this number is too high, then this T delta S, I'm hoping you guys can see my mouse as well, then it won't be spontaneous. And similarly for this one, if the disorder is high and so when So this will be a positive number, and subtracting another positive number, if this number is too high, then it will become, or sorry, when this is a positive number and you subtract another positive number, if this is too low of a positive number, it'll come out positive, which means it's not spontaneous. Okay, so there's a state called equilibrium when it's neither positive or negative as well. And this is when T delta S is greater than delta H, and it's when it's equal to delta H. And as you can see here, as you go up from the equilibrium, as the temperature raises, it's a spontaneous state, and that's when T delta S is greater than delta H. And when it goes lower from the equilibrium, it's a non-spontaneous state. And also, like H and S, G is also a state function, so we can use Hess's law. As I kind of talked about earlier, since the journey doesn't matter, you can subtract the sum of all the reactants from the sum of all the products. And then also in class, we kind of talked about how this is actually happening in our bodies, and it's through Gibbs free energy that we're able to pair conflicting processes and able to get some useful work to use within our bodies. Look up. Okay, so I was just going to talk about some of the practice problems from the homework as well, just as a reminder. So one of the questions was, what are the signs of delta S, delta H, and delta G for the formation of dew on a cool night? And since the dew is going from gas to liquid, the liquid has a lower entropy than water, and so the change in S is going to be negative. And this process is exothermic, so the change in S is negative as well. And if we remember right from that, we know that delta G is also going to be negative, meaning that it is going to be a spontaneous process. Let me see the other one that I wanted to go over. What are the signs for delta S, delta H, and delta G when making ice cubes from the freezer? So this is a liquid going into a solid. So delta S is going to be, delta S is that disorder. It's going to be negative because the solid is formed from liquid, which has a lot less entropy in it. And then delta AH, which is endothermic, exothermic, is going to be negative because heat is released during the phase change. And since it's released, it's going to be exothermic. And then delta G is negative because in the freezer, this process occurs spontaneously, which we can figure out because we know delta S and delta H. Okay, and then I also wanted to do some practice with what is spontaneous and what is not, just right off the bat. I kind of gave some examples at the beginning, but some from the homework were whether muffins rise in the oven, And muffins, they are spontaneous at a high enough temperature, but if it's too low, then it's not spontaneous. Nothing will happen. And that makes sense because if you put muffins in an oven and it's cold inside, nothing's gonna happen. But if you turn the heat on, then there's obviously a reaction that happens and continues to happen until they eventually burn if you don't do anything about it. And then the soup gets cold. Hot soup spontaneously cools before being served. As soon as you take it off that heat source, it'll start to cool down. And yeah, that is pretty much all I have. Thank you guys for listening.